Creating high-resolution, realistic 3D human avatars from simple natural language prompts is now a mature, highly reliable process. But when you feed those exact same text to 3D generative pipelines a prompt for an anime or stylized character, the architecture collapses. This reference image highlights the baseline artistic conventions of 2D anime media. The proportions are highly specific, relying on massive, expressive eyes and severely simplified nose and jaw structures. Even as we switch to this upset expression, the stylized geometry remains consistent. These precise structural exaggerations are required to convey the specific aesthetic and emotional range of the medium. The ultimate objective of current research is translating that precise 2D stylization into a fully realized 3D volume, like this rendered character model. Because foundational AI training datasets are overwhelmingly dominated by photographic data, the resulting network priors are heavily biased toward real human anatomy. To achieve non-photorealistic geometry, developers had to abandon text prompts entirely and regress to feeding the model's raw image data. This diagram maps the standard text-to-3D generation pipeline for realistic human avatars, allowing us to pinpoint exactly where the architecture rejects stylization. The SMPLX parametric model in the top section provides the baseline skeletal guidance. It mathematically enforces realistic human proportions. Moving down to the appearance control block, ControlNet and a 2D diffusion model interpret the text prompt to condition surface visual details. Finally, on the left side, the Instant NGP node takes those visual references and reconstructs them into a coherent 3D mesh. The pipeline fails because extreme stylization breaks the physical mapping of the canonical space. The standard skeletal model natively rejects the proportions required for massive heads and tiny noses. With the skeletal mapping physically unable to accept non-human proportions, researchers were forced to bypass parametric modeling entirely. They resorted to brute forcing the 3D shape using multiple overlapping 2D reference images. The first major workaround was CONAR, requiring 4 perfectly aligned reference images to construct a 3D shape. It achieved this through ultra-dense pose mapping, forcing a mathematical correspondence between 2D landmarks and the 3D body surfaces. While accurate, this creates a severe data acquisition bottleneck. Procuring 4 specific, highly overlapping views of a single character in a consistent pose is rarely practical in real-world use. Nova 3D drastically reduces this input burden, requiring only 2 non-overlapping images. Zooming in, its volumetric generative network infers complete volume strictly from front and back visual data. Cutting the input data in half introduces noticeable artifacts. Without 4 overlapping views, the neural network entirely loses the high-frequency data, resulting in smoothed-out facial features and simplified clothing textures. Every time you reduce the raw input data, you strictly degrade the output mesh fidelity. It establishes a direct mathematical trade-off between the accessibility of the pipeline and the geometric accuracy of the final model. To maximize accessibility, research shifted towards single-view reconstruction, attempting to generate a complete 3D mesh from just one reference image. To pull this off, the network relies on viewpoint lifting, artificially hallucinating the missing visual data by extrapolating multiple camera angles from a single FLAC input. The Character Gen framework abandons the parametric skeletal model completely. Instead, it extracts 2D key points directly from the input image to guide the 3D generation strictly in a neutral A pose. Character Gen's transformer-based model generates detailed meshes in under a minute. However, the side and back profiles reveal catastrophic self-occlusion artifacts, where overlapping elements block the geometry. Discarding the parametric model allows for rapid generation from minimal data, but it sacrifices the precise shape and pose controls strictly required for downstream animation and rigging. To fix the artifacts caused by treating the avatar as one monolithic block of data, researchers introduced the SDGen architecture. SDGen operates on semantic decomposition. It isolates the 3D representation into distinct interpretable attributes, like the hair, the body, and the clothing shell. By treating these elements as separate attributes, the network applies multi-layer mesh refinement to each component independently, allowing for granular structural control over complex areas. Processing semantic attributes independently carries an extreme computational weight, requiring 3 times the processing duration of monolithic models like Character Gen.
Even with isolated attribute processing, standard single-view inputs hit a hard ceiling on resolution quality, regularly requiring manual post-editing to fix surface distortions. Single-view architectures pushed image-based inference to its absolute limit. Attempting to hallucinate perfect high-resolution geometry from a single flat image is computationally intractable without modifying the foundational priors of the network itself. The overarching objective was always to escape deterministic image inputs entirely, allowing users to generate high-fidelity 3D stylization using strictly natural language prompts. This red jersey avatar demonstrates AnyDream's accurate topological stylization. Meanwhile, this kimono avatar proves the network generates complex volumetric depth from text alone. To accomplish this, developers modified the general pipeline diagram with two overrides. First, an anime adaptation module in the 2D diffusion model blocks photorealistic priors. Second, a custom cell shading loss function in the NeRF generator forces non-photorealistic surface topologies. By surgically retrofitting the standard realistic pipeline with stylization-specific overrides, AnyDream successfully divorced high-fidelity 3D generation from the strict requirements of reference imagery. With static stylization largely solved, the next open challenge is dynamic, physics-based animation. Generating accurate meshes doesn't automatically yield rigging. This lack of rigging is especially problematic when dealing with the complex physical characteristics of anime-style hair and flowing cloth. Standalone physics solvers for stylized motion exist. However, binding them directly into the generative NeRF or Gaussian splatting loops breaks computational budgets.
Resolving the original stylization bias require years of brute force iteration, moving from multi-view to single-view image inputs, until algorithmic efficiency finally caught up. When foundational AI training fails, structural workarounds can bridge the immediate gap, but taking the final leap forward always requires returning to the core architecture and rewriting the